It's a pleasure to be able to talk to you all. I hope that you will enjoy the conference, the workshop today, and the beautiful location. I'd like to thank the organizers for inviting me. So what is adversarial machine learning? The description of adversarial machine learning on this workshop's website considers threats or adversarial behavior. It states, AML is concerned with the design of ML algorithms that can resist security challenges, studying attacker capabilities, and understanding consequences of attacks. There's a more general and pluralistic definition on the NIST website, where there's a page documenting an effort to standardize and taxonomize adversarial machine learning. By the way, the existence of such an effort is clear testimony of the diligent work of your community, so congratulations. The website states, adversarial machine learning is the process of extracting information about the behavior and characteristics of an ML system and or learning how to manipulate the inputs into an ML system in order to obtain a preferred outcome. So what is arguably neutralized in this definition is the adversarial aspect of the topic, but it's just as good. The report offers a standardized vocabulary and a taxonomy of adversarial machine learning attacks, and it will discuss mitigations that work along with their limitations. This figure from the report separates out core aspects of model availability, integrity, and privacy. Around each core are adversarial threats. For example, model poisoning threatens the availability of a model. Black box evasion threatens its integrity, and membership inference is a threat to the privacy of a model's data. I expect that everyone here at this workshop is able to place their current and past work in these contexts. The next question I pose is around the impact of adversarial machine learning. The workshop description provides that also, and I really like the statement. It notes, first, improvement of trustworthiness, such as better robustness, explainability, and fairness. And it mentions how AML informs other machine learning paradigm advances and stimulates questions that cross-cut across different topics, such as styles of programming or HCI. The third part of the workshop description motivates many of the submissions and invited talks today. It also reflects how AML continuously reigns as a contemporary hot topic. It focuses on the trends, challenges, and applications of adversarial machine learning in the context of the latest machine learning offering, large foundation models, which I will refer to often as LLMs, or large language models, or LFMs, and sometimes FLMs when I'm dyslexic. So here's the agenda for the remainder of my talk. Let's consider the case for focusing on large foundation models. Then let's cover a topic that's a lot more prominent with large foundation models than it has been with deep learning, and that's the potential harm that could come from operating these models. I plan to then discuss red teaming, both as an approach for cybersecurity and an approach for LFM safety. And to end, let's ask, what are the broader intersections of adversarial machine learning with large foundation model safety and security? Now, what is the case for paying so much attention to foundation models? Well, clearly, one big reason is their startling advances. I like this slide from Life Architects because it has a row for models of different parameter and training set complexity. And on each row, it shows some of the new achievements of these models. There's achievements along a large swath of activities, like linguistic puzzles, reasoning about shapes, causal judgment, reflection, logical deduction, coding, spatial reasoning, even college level exams, the bar exam. So you can talk to these models and they largely respond very well along a huge set of dimensions. That's why we're paying so much attention to them. And let's not forget that they're also multimodal. They can handle code and images. Here's a remarkable example among many of text-based image processing. There has been accelerating growth with new models, and training piles and capabilities are emerging quickly. And LFMs promise to impact the nature of work that is done by AI. Here's just a short example of their impact on marketing and advertising technology. And they're also going to change what really work is for all of us. Note with this slide, the emergence of AI-enabled knowledge workers. And to the right, the types of strategic and tactical work that remain for humans after LLM-supported work arrives. The social impact beyond the workplace is also immense and disruptive. This slide depicts the risks and benefits of large foundation models for the environment, organizing them left to right into negative and positive, and downwards into direct, like energy consumption, and indirect impacts, and impacts on research into the environment. I anticipate that across all fields, this sort of assessment is being conducted. Finally, amongst all the excitement and anticipation is the possibility of LFMs inflicting harm. Harms could be adversarially initiated, posing a security risk, or they could be related to unsafe behavior arising from the model operating. So let's talk about harm and security and safety in this context. First, what's the concern? I don't want to venture into the arena where the artificial general intelligence of the model is debated or its potential for singularity is under question. I don't want those to be the drivers they are not my drivers for concern about harmful behavior from LFMs, but a pragmatic concern that I do have, and one that is less predicated on the arguable definitions of what artificial general intelligence is this. We have algorithms that baffle us, and we've given them the ability to make decisions very fast. And this fast decision making can result in consequences that are very hard to stop. And here I butcher a quote from Norbert Wiener, who did really seminal work into thinking about machine safety right back in the 1950s and 60s. So where does the responsibility for large foundation model safety and security lie? Who are the power brokers in this arena? Most recently, power over control and assessment of harm has been held by the model makers, such as OpenAI and DeepMind. Hopefully, for balance, open source enterprises will join the ranks. OpenAI made overtures to government here in the USA, and just this week, the Biden administration and a group of makers wrote some sort of MOU around assessing and limiting their potential harm. So the government plays a role as a power broker. And finally, I've squeezed in at the bottom, the academy, researchers in university, many of whom are here in the room. We can contribute to assessments and mitigations of harm, leveraging the many threads of work we do, such as explainability, or more broadly, adversarial machine learning. We may, in fact, be the best positioned to be objective and informed, and we may need to take on the responsibility of calling any bluff of the makers and LFM-based service providers who are going to prioritize business models over other aspects. We may also need to step up and educate and inform the dialogues and policy efforts that are emerging. This potential for harm from the operation of large foundation models sirens a call for better safety and security. Safety and security are sometimes confused with each other and conflated. So I want to clarify by differentiating them in terms of their respective goals. The aim of safety is to prevent a system from impacting its environment in an undesirable or harmful way, typically to protect human lives, the natural environment, or assets. The aim of security, on the other hand, is to prevent often adversarial environmental agents or conditions from impacting a system in an undesirable or harmful way. These definitions are verbatim from a report written by Trail of Bits, and I highly recommend you taking a look at that report. I'll say more about it later. So what are our current approaches to LFM safety and security? Let's first talk about safety. Model cards provide documentation, auditing provides checks, and they both offer better transparency. Bounties enlist a broader community in finding hard to identify risks. Then, at a system level, lie risk frameworks, which are going to be extremely important because of what they offer in comprehensibility and structure. So let's look a little more at them. A good resource for learning more is this Trail of Bits report that I mentioned earlier. It speaks of a concrete operational envelope that helps developers and auditors assess potential risks and required safety mitigations. NVIDIA has just released a web report on what it calls information security assessment, which covers assessments of model harm at multiple levels, spanning from training to deployment. It's well worth a read as well. And if we're going to get security right, we may also have to translate and transfer risk analysis from other fields. Here's an example where Paro provides a perspective of risk in two different dimensions from earlier ones. It talks about the complex versus linear interactions of a system and systems which by design have tight versus loose coupling. So there's a lot of food for thought here. Let's next talk about security approaches to large foundation model harm. I've first listed adversarial machine learning because it can uncover vulnerabilities with adversarial actions. My research agenda looks specifically at adversarial intelligence, the human behavior that drives intent, strategy, and tactics that result in adversarial threats, as well as the learning and adaptation that drives adversarial dynamics, which arise from two sides, offense and defense, engaging with conflicting objectives and incorporating feedback into updated strategy or tactics. My goal is to computationally replicate adversarial intelligence, hence the artificial prefix on adversarial intelligence and the acronym AAI. To compare AAI to AML, I would say that AML is algorithmically tactical. It focuses on the algorithms that threaten models, making it a part of AAI. Both AAI and AML work in the domain of cybersecurity. AML focuses on models, while AAI, being broader in scope, includes models and also extends to the security of networks and network endpoints and devices. In this respect, some of my work is adversarial machine learning. I've looked at attacks on malware detectors and query minimization and black box attack settings. Another part of my work intersects with adversarial ML in a different way. We have a project named Brawn, in which we've been uniting all the web-based sources of cyber threats, vulnerabilities, and mitigations. In the next year or so, I hope to integrate into Brawn a web-based source of adversarial machine learning techniques and tactics. Those are the ones that show up in MITRE's Atlas database. Brawn assists with threat attribution in cyber hunting. Its sources are primarily text-based with some code as well. So enlisting the support of large language models in Brawn promises really powerful advances in both threat attribution and hunting. And that's been a part of my group's most recent work. Finally, there are parts of my work in adversarial intelligence that are outside the scope of adversarial machine learning, such as studying dynamics, where I use reinforcement learning and evolutionary algorithms to look at the cyber arms race. One aspect of my work that I want to talk about here, though, is automating cyber red teaming. This intersects with red teaming being described in the context of LFM safety efforts. What is red teaming in cyber? It's friendly efforts to identify security issues by posing as a threat actor. At its narrowest, it's script-based penetration testing that might be done by script kiddies. More sophisticatedly, it is a goal-directed threat actor with behavior that includes improvisation, hiding, potentially deceiving and covering tracks, and acting stealthily to disrupt, steal, or ransom a sophisticated, well-defended cyber asset. It's about threats from outside. Hence, red teaming in cyber is about security, and that's what brings it in line with adversarial machine learning. LFM red teaming, in contrast, is addressing safety. So it actually may be inappropriate to use the notion of red teaming in LFMs for safety, and maybe fuzz testing from software engineering might be better, but I'm not here to police terminology. What I'm going to talk about first is safety red teaming for LFMs, and I'm going to reference these two publications, which I refer to as DeepMind and Anthropic in the slides that follow. For LFM safety red teaming, you could think of there being a tester with test cases. The testing and test cases can be prepared manually, but more efficiently, a FLM is used. The target of the testing with test cases is another language model that is being assessed in terms of whether its replies to prompts are harmful in some way. Red teaming research for safety of LFMs seeks good testing, that which uncovers all potential harms of a model. Thus, red team performance criteria is diversity and difficulty of the test cases. I like to sometimes call the test cases candidate threats or just threats, because that's what they are. They're basically threats on the model in terms of it operating outside its safety envelope. And that's what's being, this whole organization is what's being illustrated in this feature on the left, taken from the DeepMind paper. The authors use a chatbot named Dialogue Prompted Gopher, DPG, as to support red teaming. That's the creation of test cases. And they also use DPG as their target. DPG is a pre-trained 208 billion parameter transformer language model, and it's been trained on internet text and other sources. So the red LM shown here semi-automatically finds test cases where the target LM replies in a harmful way. So candidate threats or prompts are scored for performance by passing them to the target LM and then taking the target LM's reply and passing them through a classifier, seen here in the rightmost column, which has been trained to detect offensive content. And with this setup, the authors are able to uncover tens of thousands of offensive replies. And this should look like fuzz testing to you, right? This is looking for test case coverage and help in finding out defects in a piece of software. To analyze this system performance-wise, you can look on the right. So here we have a plot, and the y-axis measures the diversity of each method's test cases. I would call this test case coverage in the software sense. And the x measures their difficulty, how many result in offensive replies. Just briefly, the methods for red teaming range from zero-shot prompting, using unsuccessful prompts to generate better ones, to unsupervised learning, and to reinforcement learning. And the authors actually tried 3 variants of reinforcement learning that differ in their weights within a loss function used in training that combines a diversity objective with a difficulty objective. And what we see here is a trade-off or Pareto front in this experiment. It shows that if you want, in this case, when the test cases have better coverage or they're more diverse, they're actually not that good at eliciting offensive replies. But when the reinforcement learning method is used, it can elicit more offensive replies, but it tends to be focused and on particular ways to elicit that harm, and it doesn't offer as much diversity in its test cases. That's the first analysis, and it's listed here, but there's more analysis that can be conducted. The test cases or prompts that have successfully elicited harmful replies can be examined and clustered. And here we find that generated questions compare favorably to questions written by paid human adversaries. Specific harmful phrases and data leakage test cases can be generated, and the harmful replies and successful test cases can be analyzed. Moving to the Anthropic paper, there's an analysis that has clustered the threats by topic and colored them by performance. The Anthropic paper actually expanded on the target space and looked at how harm differed across different targets that varied in size. And the question being, like, as a model gets bigger, is it easier or harder to successfully red team attack it and force it to reply with harmful outputs? So let's just attend to the leftmost plot. On the left axis are different target models that graduate in size, as measured here by number of parameters. So there's 3 groups of those. And on the y-axis is attack success on the target. If you just look at the one size, the first block of one size, is what you see are 4 types of models that can be distinguished by their colors and by their output layer design choices. And what we can observe is that plain and prompted LMs are very easily attacked, but rejection sampling models fare a bit better. And the ones that have been fine-tuned with reinforcement learning here are quite robust to adversarial safety threats. Interestingly, this ranking holds across model sizes. So if you sweep your eyes and you check the blue columns across all 3 sizes, or the orange or the green or the red, you see a little variation. The other 2 figures are actually also very interesting, but I'll let you study them offline. So this is safety based red teaming. And what is the overlap with cybersecurity driven red teaming? Well, one interesting aspect and overlap is that they both now use large foundation models. I'm going to show you the design of our work in progress red team agent, and it's LLM supported. In one of our first explorations of trying to figure out how to use LLMs, we realized that we could prompt an LLM with a narrow red team task. And by chaining prompts and replies together, we were able to ask the LLM what a network intruder should do immediately after penetrating a network. And what's super impressive here is that the LLM accessed threat knowledge right down to pulling a technique from the MITRE attack matrix, which is contextually correct. And it provided the command that should be used by the red team agent. When we gave the LLM more network information, it further was impressive when it integrated that information and set up the command with specific arguments that reflected that information. So it gave us the IP addresses that we needed to use the nmap command. And that means we can really use the LLM to obtain commands that we can directly execute. This really kickstarted our current work on LLM-supported cyber agents for red teaming. I'm showing how our work sets up a red team cyber agent that interacts with a network, and on the other side of the network is a blue team defending it. Prior to using LLMs, our agents simulated their technique level, that is, the commands they would issue on a network. And they operated on a model of a network, which then provided us with simulated results of those commands. With the LLM support, we're able to move from simulation and modeling to execution of techniques in a network sandbox. And this dramatically ups the realism of the situational context. It allows for us to think about more intricate interactions with the network and beyond it with the defensive measures that network defenders take, such as employing firewalls, gathering alerts, detecting malicious activity, and even mitigating effects on the fly reactively. So our red agent is set up to prompt an LLM and ask it what it should do. And it uses its replies to execute commands and scripts that come from a common and open tool environment called Metasploit. And it does so by being sort of implemented inside a Kali Linux box. And that is connected to a containerized network environment that we control. Here's the actual network that we control, or sandbox. Note that it's a Docker environment that can capture, that in which we can put, defensive tools like Splunk or intrusion detection systems, and we can actually capture from them the real observables that they have of the actors' actions. We needed a design for our agent that would interface effectively with the LLM to use it to plan sequences of actions, like steps within a kill chain. For this, we took inspiration from prior work using LLMs to support robotic sequential decision making. The key insight here is that a red agent is embodied or situated much as the robots are in these papers. It senses the network to gather observations of its state, and it acts in the network much as robots sense and act in their digital or real environments to complete the tasks that fulfill their goals. So we integrated this level of looping LLM use with the logic of cyber threats. We have the selection of tactics that move an agent along the threat's kill chain. And the agent uses the LLM to select a tactic, then it uses it again to translate that tactic to a command it can execute on the network. And it finally uses the LLM again to parse the output of the command that we gather from the network. This report is what can be taken to the start of the loop, tactical action selection, to iterate again and move forward. So our designs are pretty preliminary, and our experiments are still small, but we're making some progress towards more autonomous and sophisticated red agent behavior. It has involved a lot of prompt engineering. Here's the sort of templating we use. It's modular, so we can use it consistently throughout the agent design. And here's an illustration where we step through just 3 steps of a kill chain, each time using the plan, act, report loop that I showed you earlier. That's been specialized, of course, to the cyber domain. Like the safety work, we can analyze the effectiveness of the agent. I won't go into the details, but this information tells us how to improve the LLM support, and it guides how we're going to move to broader scenarios. And if you sort of take a look at our initial findings, our list has 3 green check marks, which are very positive, and they're around automating situational awareness, allowing explicit tactical execution, and providing human readable results. But we have lots of work ahead of us. In particular, we don't know how much cyber knowledge is within the LMs and what the implications are. We also have typical challenges related to hallucinations, context windows, and novelty. So returning to the original slide with the intersection being mentioned, I hope you can see how LLM support for red teaming, whether for security or safety purposes, is what unites the different endeavors, one by large foundation model makers and one by AAI research like my own. Red teaming, or stress testing a system in the safety sense, is similar to friendly cyber agents that try to launch a threat campaign against a network. When FLM's safety measures are in place, perhaps they can function as the blue side. What would adaptation and an arms race dynamics be in this safety context? I'm not sure, but it's an interesting question. Another interesting question is that on which this very workshop focuses. How might adversarial machine learning, which is a security-driven problem, transfer to the security, and I say even the safety, of LLMs? I can't be present to hear all the presentations today, but I certainly intend to check out the work to find out some answers. Before concluding, allow me to thank you for your attention. I'd also like to call out work by senior members of my research group, Stephen and Eric, as well as Heidi and Dylan, with whom I have recently been discussing LLM safety. I'm eager to interact, so I provided my email, and I wish you an informative and stimulating workshop and a great time at ICML.